Okay, the last unit in this kind of subunit of chapter 11 is 11.6, area of regular polygons. Central question, how can you find the area of a regular pentagon? Remember, regular polygons, equilateral, equiangular, pentagon, 5 sides here. So that's something we'll be able to answer at lesson's end. First of all, vocabulary for regular polygons. We have 4 key vocab items: center, apothem, radius, and central angle. So if I go ahead and I will make a pentagon that's pretty close to regular, not so perfect there. The center of the polygon is a point inside that would be the center for a circle that would touch each vertex. So I'm going to go ahead here, I'm going to say, hey, there's the center. Alrighty. The apothem is a segment from the center to the midpoint of one of the sides, and it's also perpendicular, okay? And it also bisects the angle that the apothem touches that side. So the apothem here is this perpendicular piece. The radius is going to be from the center to a vertex, as you can imagine the circle inscribing the regular pentagon here. So that's a radius. And then finally the central angle, not named after Central High School, but it's really the angle formed by 2 radii with a regular polygon. And again, that central angle is going to be determined by 360 divided by the number of sides we have. So that's kind of a general rule here, and that's something that we're going to use periodically along the way here. Now moving further, as we go here, for us to sketch a regular hexagon, though this is different than what you have on your notes here. You have a regular quadrilateral with a perimeter of 100. So let me fix this. Regular quadrilateral and a radius of 17.7. Sorry about that. So regular quadrilateral, 4 sides for a quadrilateral. Regular, I'm going to mark these here. This is really going to be a square. Okay. And if I take 100 divided by 4, I get 25. So I just put 25 out here for one of the sides. And then the radius, again, is that length from the center of the polygon to a vertex, and this is 17.7. So we could put the units on there as well, but kind of a tight squeeze there. Regular octagon, octopus, 8. So 1, 2, 3, 4, 5, 6, 7, 8. That might be one of my better ones. I'm not going to go ahead and mark everything, but all the, I guess I will here. Mark this. And again, all the sides congruent. And again, the center here. And the apothem is 3.4, so I'm going to run that to the midpoint of a side. I guess I do that. And 3.4. Okay, so again, just to get some of the terminology down with an example here. We do have a regular polygon area formula that works for all regular polygons, and it's basically based on the thought that a regular polygon is made up of 1, 2, 3, 4, or n triangles that are isosceles, with the apothem being the height and the side length being the base. And likewise here, I'd have 1, 2, 3, 4, 5, 6, 7, 8 triangles. Again, the apothem is the height of the triangle, and the side length is the base. So if I think about, I've got n triangles, which are 1/2, the side is the base, and the apothem is the height. That's really our formula for the regular polygon. So it says here that the area with an apothem of A, side length of S, and N side, so if I've got N, S, and A, is 1/2 S, A, N. And I just put the letters in a different order. 1/2 SAN is kind of a good way to remember it. If I take the number of sides times the number of sides times the length of sides, I get perimeter. And so another way is we could say 1/2 of perimeter times apothem. So again, there's two possibilities here, 1/2 SAN and 1/2 PA. So I'm going to write those both down, 1/2 SAN or 1/2 perimeter times apothem. So those are kind of the two formulas that we're going to be using. Now moving on here, just to name some items here, G is the center. We actually have two radii, they're right here and they're right here. So I could call it GB or BG, and AG would be two examples of radii. The apothem is right here in blue, so that's going to be GH, that segment there. And now finding some angles. This is a 1, 2, 3, 4, 5, 6. This is a hexagon. So the measure of angle AGB, this angle here is basically a central angle. So it's going to be 360 divided by 6 gives me 60 degrees. Now finding this next angle, the measure of angle HGA, HGA is this angle right here, which is half of my central angle. So I'm just going to take 60 times 1/2, or divided by 2, and I get 30 degrees. And then finally, we're asked about angle BHG, and that is part of the apothem side length meeting, so that's going to be 90 degrees. So again, these angles are going to be important as we continue to find out areas of these triangles and then multiply by the number of sides. Now moving on and using our area formulas for a regular polygon, again it's based on triangles. We'll do a couple of these. I think we'll do maybe the first one, A, and the last one, C. A decagon. Now we do have to recall some of our facts of earlier polygon work. A decagon has 10 sides. So I have this, I have this, and I have this. I have my apothem, and I have my side length, so I have everything I need. And if you notice, we do have approximation symbols here. Regular polygons cannot just have any old measures. They have to be carefully calculated, and they rarely come out to be integers for all. We'll have an integer for the number of sides always, but a lot of times we're going to have some rounded values because of the complexities and the angles that are involved. So I'm going to go ahead here. This one's ready to go. 1/2 SAN is the formula I'm going to use, and I'm going to plug in then. 1/2 S is 3.7. Apothem is 5.7, and the number of sides is 10. And since this is a calculation made up of approximation, my answer is going to be approximate. So I'm just going to go ahead here and say this is about 105, and in this case it's area, so it's going to be centimeters squared. And it's okay to round these to the whole units. It depends how you round. The reason I'm using parentheses to show multiplication is the fact that with these decimal points, they can be at times confused with multiplying dots. So we'll kind of just use parentheses a lot here. Like I said, we're going to do choice C here. This seems like it has limited information here. But again, let's go ahead here. A hexagon is 6 sides, so I have that. I have that. And what I'm looking for now is what is my apothem. Now that's going to take a little bit of work here because it's just not given to us here. So I'm going to sketch a hexagon. You want to make it decent size, so you can go ahead and do some work along here. Remember, the apothem would be something like this. This is my A. And again, I do need my side length here, so I'm going to take 72 divided by 6 gives me 12. So each of my sides are 12. Except this one I'm going to break up as 6 and 6, because again, the apothem is a perpendicular bisector to a side. And now I'm going to go ahead here and form this right triangle. So now we should be able to approach doing something either Pythagorean or SOHCAHTOA. Now, I don't know what the radius is going to be, but I can figure out this angle. It's going to be, I'm going to bring that up here, 360 divided by 6 to get the central angle, and then that equals 60. And then I've got to take 60 and times 1/2, because I'm 1/2 of those degrees. So this ends up being a 30-degree triangle up here. Hard to squeeze that in here. So that's 30 degrees. And now we can either use special right triangles, 30, 60, 90, or I can take this angle with this and say that the tangent of 30 degrees equals 6 over A. And we can go ahead and use our proportion work with the built-in trig tables in our calculator. And when we solve this, we take 6 divided by tangent of 30, and I'm going to get an apothem of about 10.4. So now I have my perimeter and my apothem, so I'm in pretty good shape here now to go ahead and determine the area. So I'm going to go ahead, area is 1/2, perimeter times apothem, A equals 1/2 of 72 times 10.4. And again, I'm going to parenthesize these because the decimal point can kind of be a little bit disturbing. And so I'm going to calculate this, and I'm going to get about 374 feet squared. And again, fairly complicated, but step by step it's not so bad. At this time, I'm going to go ahead and leave A4s alone, and you will have some time to work on those. But before we do that, let's take a look at this final problem here. Find the side length of a regular 20-gon. So n equals 20, key information there, with an apothem of about 80 feet. So A is about 80. And an area, big A, and here's the importance of using proper capitalization or non-capitalization here, is we have 20,000 square feet. So they want us to find the side length. Well, that's just our S. So I'm going to go ahead and write my formula out. I'm going to use the SAN version. I know I have 20,000 equals 1/2. Side length I don't know. Apothem is 80. And number of sides is 20. In this situation, there's only one unknown, which is perfect for us to solve. And at this time, I like to do some combining here. Half of 20 is 10. 10 times 80. I can divide both sides by 800 and take care of the whole kielbasa here. So this, and this, cancel that. And when I go ahead and finish out, I'm going to get S is going to be about, because we're using rounded values to begin with, so we're going to have a rounded result, is going to be 25 feet. Now that's a pretty big 20-gon. An awful lot of square footage there. Well, this ends the video part of the lesson. Now you will have some time to do a couple of the A4 problems. Thank you for your time.